All right, so our last distribution was the exponential distribution, and we showed how that came from the Poisson process. We thought of it as the distribution of the first distribution of the first arrival in a one-dimensional Poisson process. Related distribution is what's called the gamma distribution, which we'll talk about now. So the gamma distribution, we're going to consider a Poisson process just like before. In particular, a one-dimensional Poisson process, which we'll call a Poisson arrival process with intensity lambda. And we're going to let WR be the waiting time until the rth arrival. Then, in this case, the probability that the rth arrival happens after time t can be expressed in terms of the count process, the Poisson counting process, to say that the number of arrivals before time, up between time 0 and t, is at most r minus 1, which we can express as a sum of Poisson probabilities. So that count is Poisson with parameter lambda t. And so it's e to the minus lambda t to the j over j factorial, where we sum from j equals 0 to r minus 1. That doesn't really get us anywhere, at least initially, because we don't have a closed form for that expression. But if we want to compute the density, so we can think about, okay, what is the density? There's a couple of ways to get this distribution, but one is to think, okay, in terms of the density, let's use the infinitesimal approach. So let's write the density as f sub r of t dt. For small enough dt, this is approximately the probability that WR, the rth arrival time, is between t and t plus dt. In order for the rth arrival time to occur at exactly between t and t plus dt, because dt is such a small period of time, so let's draw this out a little bit. If we imagine that r is, say, 4 in this case, then in this case, WR is here. Right? So in order for this to happen by the Poisson process rules, it's extraordinarily unlikely, to the point of being really impossible, as dt gets small, for there to be more than one occurrence within a very, very small region. We assume that there's only at most one hit at any given time. So in order for the rth arrival to occur exactly at time t, which is essentially what this is saying, we would need the number of arrivals up to time t to be equal to r minus 1. And then we would need the number of arrivals between t and t plus dt to be exactly equal to 1. And because these are counts over non-overlapping intervals, they're independent. And so once again, we can use the independence property of the Poisson process to calculate these probabilities. So probability that there's exactly r minus 1 in the first t units of time is e to the minus lambda t to the power r minus 1 over r minus 1 factorial. That's just from the Poisson probability times the probability that exactly 1 occurs in a length of time dt. So that's e to the minus lambda dt to the power 1 over 1 factorial. And so if we write this and we think of dt as being small, then this simplifies to, we get an extra lambda, so we have lambda to the r t to the power r minus 1 e to the minus lambda t over gamma, the gamma function of r, which I will define. Well, in this case, we just define gamma r as r minus 1 factorial, but we'll define that more generally a bit later. But this is now the density. So this is the density of WR. Okay. So a random variable, and this is what's called the gamma density, a random variable W with density given here, and this is on non-negative values of t, has the gamma distribution with shape parameter r and intensity lambda. And the way that we write this is we say that W is gamma r lambda. One thing to notice, or one way to think about the distribution of a gamma, is that in this case, WR is, it's the time until the time until the rth arrival is the sum of the times of the inner arrival times, right? So this is A1 plus A2 plus A3 plus A4, right? Where the A2s, these A variables are inner arrival times. It's the time between arrivals. And the inner arrival times are, so WR can be expressed as T1 plus T2 plus TR for T1 through TR IID exponential lambda, because these are the inner arrival times in a Poisson process, and by the exponential property, by the memoryless property, when arrival occurs, the Poisson process starts all over again from that point, because of independence of the increments in a Poisson process. So the waiting time from the first to the second arrival is the same distribution as the waiting time till the first arrival, which was exponential lambda. So the gamma distribution is the sum, gamma r lambda can be thought of as the sum of r independent exponential, the sum of r independent exponential lambdas. Similar to, and for a similar reason to what we saw for the gamma distribution, if W is gamma r lambda, then if we define X to be lambda times W, well, this is gamma R with parameter 1, right? Just like in the exponential case, if we rescale by lambda, we get a standard, a unit rate exponential, and in this case, this would be the sum of R independent exponentials. Okay. As far as the moments or the first couple of moments are concerned, if X is gamma R1, then the expectation of X, well, we could try to integrate it directly, but we might as well utilize the property that X is the sum, is equal in distribution to the sum of exponential unit rate exponentials, for which the mean is 1. And so this is R times 1, which is R. The expectation of, for the expectation of X squared, well, we can actually just calculate the variance directly. The variance of X is the variance of T1 plus TR. Since they're independent, it's the sum of the variances, so it's R times the variance of a unit rate exponential, which is 1. So this is also R. And from that, we can recover expectation of X squared is variance of X plus expectation of X quantity squared by inverting the computing formula. So this is R plus R squared, which can also be written as R times R plus 1. So then similarly, by the same logic, so if W is gamma with parameter R lambda, then we can express W as equal to X over lambda, where X was gamma R1. And so that tells us then that the expectation of W is the expectation of X over lambda. So that's R over lambda. And the variance of W is the variance of X over lambda. So that's 1 over lambda squared times the variance of W. So that's R over lambda squared. Okay, so that's the gamma distribution, very closely related to the exponential, which we've already seen. And we will come across certain examples involving the gamma distribution as we move through the course.